let's take a look at complex numbers. Now, probably when you think of a complex number, you think of, you associate it automatically with the square root of -1, I. But let's broaden our understanding a little bit, and let's think, when we think of a complex number, let's think of it this way. Let's think of a number that has a real part. This is just a real number. It could be anything, 5, 7. And then we have an imaginary part over here, the part that's multiplied by the I. So in other words, this would be, the real part would be X, and the imaginary part would be Y. And this is how we'll denote that. Okay, the real part, the imaginary part. So an example would be this. We have z equals 3 plus 2i. Here we have the real part is 3, the imaginary part is 2. Here's another one. Here we have -2i. Now notice here the real part is 0, the imaginary part is -2. So you can have, you don't have to have you could have 0 for x. So in this case it would be like 0 plus -2i. Now also, you don't even have to have an I part. You don't have to have a non-zero imaginary part. So notice here. Here we have z equals 5. The real part is 5 and the imaginary part is 0. So the numbers you've studied up until this point have all been complex numbers. 3 is a complex number. Pi is a complex number. Those are numbers where the imaginary part is 0. So we broaden our understanding of what complex numbers are. The real numbers are a subset of the complex numbers. Now, let's notice that here we have a real part and an imaginary part. We have an x and a y. Well, that kind of lends itself to being able to treat numbers, complex numbers, as ordered pairs, and then we can plot them. So imagine down here on the horizontal axis, let's suppose this is the real axis. This is where we plot the real numbers. Okay? So think about this point up here. Think, we go 1, 2, 3, over 3, and up 4. 1, 2, 3, 4. So it's like we have an ordered pair with an x and a y, but we don't think of it as x and y, we think of it as real and imaginary. So the imaginary part is the y coordinate. Now we've got -3, 4. It's over here. This is z2. Notice, go over -3 and up 4. And then we've got -3, -4. We go over -3 and down 4. So see, we can have these complex numbers plotted in any of the 4 quadrants. Okay, so this is how we can deal with complex numbers graphically on a grid. Now, let's think of this distance from the origin up to this z1. We'll just look at this as an example here. So we go from the origin to z1. That's a distance here. Now we've calculated this before with vectors. We're going to call this distance the modulus. Okay? And here's how we'll write it. We'll write it as the absolute value. We'll have an absolute value symbol. We'll put z1 in there, and we have the absolute value. And what we're going to do is we just use the same calculation that we've used for vectors, where we were calculating the magnitude. We take the 3 squared plus the 4 squared. We get 25. So we say, here, this distance here is 5. That's the modulus. That's the absolute value of this, 5. It's always the distance from the origin up to the point. Now, other things we can take note while we're here, we notice that we have the real part is 3, imaginary part is 4, and we've got an angle in here, right? See, we've got an angle. And we know that the cosine of that angle is 3 over 5, adjacent over hypotenuse. Okay, see, 3 over 5. Well, if I just multiply both sides by 5, I see that I can replace the 3 with a 5 cosine theta. See that? So up here, instead of this 3, I can write 5 cosine theta if I want to. Likewise, we can do the same thing for sine. Sine is opposite over hypotenuse. And a little bit of algebra, multiplying by 5 here, just a little arithmetic really. we get 4 equals 5 sine theta. See that? So I can replace the 4 with 5 sine theta, and look what that gives us. That means that I can rewrite this complex number. Instead of 3 plus 4i, I can replace the 3 with a 5 cosine theta, the 4 with a 5 sine theta, and then notice I just factored out the 5. So this is a trigonometry form for the complex number. Now we've got to find out what the theta is, and we know how to do that. The theta, the tangent, is going to be opposite over adjacent. So the inverse tangent of that will give us theta. See? So what we're trying to do is rewrite these complex numbers in trig form. Okay, now let's look at an example. Let's look at this here. So we've got z1 equals x plus yi. So let's just kind of make it general and see if there's a way that we can take a complex number and write it in trig form. Okay? So notice all I've done is plotted this z1 up here. This is the representation, the plotted representation of this complex number. Now, notice that, of course, the modulus is right here. There's the length of this. So I just went ahead and put the modulus there. And that's what it is when we calculate it. Now remember, this is not going to be x plus y. We can't break this up and talk about the square root of x squared plus square root of y squared. No, we have to leave it like this. X squared plus y squared, and then we take the square root after the addition is done. Now, notice that cosine theta is equal to adjacent over hypotenuse right here. That means that I can replace the x with the magnitude of z1, the modulus of z1 times cosine of theta. See, that goes right there. Likewise, sine of theta is opposite over hypotenuse. See? So that means y equals the modulus z1 sine theta. And then theta is equal to arctan y over x. So this is, I'm being more general here. Okay. And then we, of course, can write the complex number this way, once we figure out what this angle is. Okay, now let's look at some examples. Let's suppose we have this complex number here, 3 minus 2i. Now, first of all, I'm going to need the modulus. So I just calculate the modulus the way I know to do it. The real part squared plus the imaginary part squared, take the square root of that sum, and I get the square root of 13. Now, I also need I need theta. Now, this complex number, if we plot it, it's going to be in quadrant 4. Because notice, we go over 3 in the positive direction, then down 2. So this is definitely in quadrant 4. Now, the reason I take note of that is because, remember, arctan is only going to give you, it's only going to have output of angles between negative 90 degrees and positive 90, not including it, right? Between negative 90 and positive 90. So if your complex number is in quadrant 1 or 4, arctan is going to give you a good angle. It's going to give you the correct angle. Okay? So here's what we have. Notice the modulus times cosine of the angle plus I sine times the angle. Or not times the angle, but I sine of the angle. Now remember that cosine is an even function. So what that tells us is that whenever you have cosine of a negative angle like this, you can just immediately write it as cosine of the positive. Okay? Sine is an odd angle. An odd function. So that tells us that sine of negative 33.69 is the same as negative sine of positive 33.69. So, in other words, a small point is I can rewrite this way. I can just take the negative out of here. Notice this plus got changed to a minus, and this minus here got changed to a plus. That's just a minor thing. This is the complex number right here. Okay, This is the trig representation. And then we were just getting fancy down here. And this is really preferred, right? It looks better. Okay, now let's look at this complex number. Now this complex number is, we have the same magnitude, but here's the thing. This one is in quadrant 2, see? We go to the left 3 and up 2. That's clearly in quadrant 2. Okay, so since this is in quadrant 2, over 3 and up 2, see, it's over here. We have to be careful because arctan is not going to give us the angle that we need. Let's look at this. This gives us that arctan is negative 33.69. That's in quadrant 4. That worked for this. That worked for Z1, but not for Z2. So what we have to do, if we're in quadrant 2 or 3, we have to take the arctan and add 180 degrees to it. That's if we're in degrees. If we're in radians, we would add pi. So our answer is the square root of 13 cosine 146.31 plus I sine 146.31. And that's how we take a complex number and rewrite it in trig form.